Hello and welcome back. We'll continue looking at section 3.2 on graphing polynomials. And here we're going to begin by looking at multiplicities and x-intercepts. So when we solve an equation, like we saw before, when we find the roots of a polynomial, sometimes those roots can happen more than once. And when a root happens more than once, when a root happens an odd number of times, the graph is going to cross the x-axis. So for instance, we know that we have a root, so we know that we're going to touch the x-axis. But if it's an odd multiplicity, we're going to cross the x-axis, either going down or coming up. Likewise, if the multiplicity of a root is even, so the root happens an even number of times, the graph is going to touch the x-axis. So it could come down, touch it, and come back up. Or the graph could come up, touch it, and come back down. So these are the rough, this is a rough idea behind whether or not a graph will cross the x-axis when the multiplicity is odd, or when it'll just touch it and turn around when the multiplicity is even. And just as a very quick example, when we look at the function f of x is equal to x, we just have this nice function. And if we were to solve this, if we were to solve the roots of this, so 0 is equal to x, well, 0 is clearly going to be a root, and it happens with multiplicity 1. So because this is an odd number, we know that we are going to cross the x-axis at 1, which is clear. However, if we look at f of x is equal to x squared, and we were to solve for the roots, we see that 0 is equal to x squared. So 0 is going to be a root of this twice, since x squared is just going to be x times x. We have two roots of 0. So the multiplicity is going to be 2, which is an even number. So when we draw the graph of x squared, we know that it does something like this. So in fact, we already knew that this 0 is when the graph will come down, touch the x-axis, and turn around and come back. It's not going to cross over. And again, we can see this if it is odd or even. So with a more complicated example, if we find the zeros and multiplicities of f of x is equal to -4 times x plus 1 squared times x minus 5 cubed, and then we can describe the graph at these roots. So when I'm trying to find the zeros, I'm trying to find when is the 0 going to be equal to all of this. And this will be equal to 0 when one of these factors is equal to 0. So this will be equal to 0 when either x minus 1/2 is equal to 0, or x minus 5 is equal to 0. The -4 can't ever be equal to 0, so we can ignore this first factor. So x could be -1/2, or x could be 5. So here are our zeros. Zeros are -1/2 and 5. So what are their multiplicities? Well, the multiplicity of 1/2 is going to be 2, because this factor appears twice, whereas the multiplicity of 5 is going to be 3, since this factor appears 3 times. So if I were to do a rough sketch of what I think will happen at these points, so at -1/2, since the multiplicity is even, I know that the graph is going to either come down, touch the graph, and come back up, or the graph will come up, touch the x-axis, and come back down. I don't know whether it's coming down or going up, but I do know that the graph is going to come down, touch it, and turn around. Whereas at 5, our line is going to cross the graph because the multiplicity is odd. Now it could be coming up or it could be coming down. I'm not sure which one, but with a little bit more information, we could figure that out. So again, we find the roots by setting the polynomial equals 0. We see how many times each one is a root. Since this term is squared, it'll be a root twice. Since this since this factor is cubed, the multiplicity will be 3. And with an even versus odd multiplicity, we'll either touch or cross the x-axis respectively. The second to last piece that we'll look at is the intermediate value theorem. And this one is very intuitive with a picture. So f is a polynomial function, and f of a and f of b have opposite signs, meaning maybe f of a is positive and f of b is negative, or vice versa. There has to be a 0 between a and b. So that's a lot of words to say the following. Let's say that we have a function, and we know that the function hits f of a down here and f of b up there. Since we have a polynomial function and our function is continuous, I have to get from f of a to f of b somehow. How can I do that? Well, maybe I come and I wiggle a little bit, maybe I don't know what I'm doing, but at the same time, I know that I have to get up here. So at some point, we have to cross the x-axis. And oh look, there's a 0 right in between. It's the same way if f of a is up here and f of b is down here. I have to cross the x-axis somewhere to get from above the x-axis to below the x-axis. I could do so multiple times. I could cross the x-axis, come back up, cross the x-axis again, and here, if I highlight in red, we'll have 3 zeros. But all the intermediate value theorem says is that there has to be a 0. There can be more than one, there could be lots, there could be hundreds of thousands, but we know that there's at least one. So if we have to cross the x-axis somewhere, there's going to be a 0. So how can we use this? So we can use this idea to show that this function has a real root, has a 0 between -3 and -2. So I don't know what my function is doing at -2 and -3, but one thing we could look for is we could see if our function has to cross the x-axis somewhere by seeing if one of these values is going to be positive and one of them is going to be negative. So let's find f of -3. This is going to be 3 times -3 cubed minus 10 times -3 plus 9. -3 cubed is going to be -3 times -3 times -3 is -27 times 3 is -81 minus -10 times -3, so that's going to be minus a -30 plus 9, and -81 plus 30 will be -51 plus another 9 is going to be -42. So if I draw this a little bit more accurately, at -3 my function value is going to be -42, so it's going to be way down here somewhere. But if I plug in -2, I have 3 times -2 cubed minus 10 times -2 plus 9. -2 cubed is -8. -8 times 3 is -24. 10 times 2 is 20, and I have 2 negative signs, so that's going to cancel out and give positive 20 plus 9. -24 plus 20 is -4, plus 9 is 5. So even though down here we're at -42, up here at 5, this is going to be f at -2. So in order to get from here to here, I've got to cross the x-axis somewhere. Now, it could be the case that this function comes up and crosses the x-axis a bunch. I don't know for sure, However, I do know that there has to be at least one root in between. So at least one root. So this is all the intermediate value theorem tells us, is that there's at least one. It could be that there's a bunch of them. And we know this because we have to cross the x-axis somewhere. And if we're going from negative 42 up to positive 5, it's got to be in between those values. It's got to be in between negative 3 and negative 2. So the last bit of how to draw a polynomial that we'll look at are turning points. And we're not going to look at this in very much detail, but essentially a turning point is where the function goes from increasing to decreasing. So for instance, here, this is called a turning point. Because our function is going from increasing to decreasing. It's going up, and then it comes down. Here is another turning point, because we're coming down, and then we're going up. It's anytime we're switching directions. And we'll see that we have a third turning point up here, which we're going up, and then we're coming down. So there are 3 turning points here. And what this tells us is that if we have a polynomial of degree n, you can have only n minus 1 turning points. And this is at most. It could be the case that you have fewer than this. So for this function, we have 3 turning points. So that means that this polynomial has to be of degree 4 or bigger. The degree has to be bigger than the number of turning points. So this function could have degree 4 or 5 or 6, but it has to be bigger than 3. So the degree has to be bigger than 3. So this is all we're going to look at for turning points, is just how many there are. And we can put all this together. So there's 5 steps to graph a polynomial. We determine the end behavior. So we look at what happens as x gets really big or as x gets really small. We find zeros and their multiplicity to know whether or not the graph will come down and just kiss the x-axis, or whether or not it'll cross through the x-axis. We can find the y-intercept to see where it crosses the y-axis. We can use symmetry to determine if this is going to be an even function or an odd function, whether it's symmetrical about the y-axis or symmetrical about its rotational symmetry. And then the last thing that we can do is just check the number of turning points. So in the final video, I will go through this function, and we will graph this without having to plot 1,000 points.